Okay, excellent. So let us get started. So we were discussing last time about guidance systems, and we were understanding that the idea of a guidance system is to provide that so-called reference trajectory for us, which we will then be using our control system to track that trajectory. But when we are doing this, finding this path of the trajectory, it is important to understand that there are different types of scenarios. One is that I have a set point regulation where I have a desired position and attitude that are constant and not changing with time, versus a trajectory tracking where we want the desired output to be time varying in a certain manner and matching with our time varying desired output. So that's where both the attitude as well as the position of the vehicle is time varying in nature. Then we talked about the idea of target tracking briefly, where we said that there is no information available about the future for that so-called target that we want to track. How do you deal with such sort of instances? And I told you that it is in these instances we will be looking at line of sight control, okay, line of sight based guidance mechanisms, and we're going to discuss that sometime maybe tomorrow. Okay. Then we went on to talk about the last part, which is the path following. So here we are not really interested in the temporal constraints, but we are definitely interested in the spatial constraints. So we do want to make sure that our vehicle can track the path using the dynamics which it really is restricted to. So sometimes our vehicle may be restricted in terms of what movements it can make and what movements it cannot make. So guidance system must take them into account when we are generating the so-called reference trajectories. And then we started off with the first thing. We started looking at the trajectory tracking, and that's where we had left off last time, where we were saying that for a trajectory tracking, there are three different methods in essence. One is I can use a low pass filters to generate a so-called reference trajectory which can be tracked relatively well. Then I said the second one could be I can use the dynamics of the craft or a low fidelity model, or a so-called less accurate, let's say, okay, as accurate as I can make it, but less accurate model of the craft in order to generate the trajectory so that all the limitations of the trajectory are automatically taken into account. So I don't have to account for them individually. And then the last part was that you can use optimization methods to bring upon these. And these were the three main topics which we said are under so-called trajectory tracking. But we had not discussed each one of them in detail. So what we are going to do today is we are going to take a look at a little bit of mathematics of what happens behind the hood when I say I want to use a low pass filter versus when I want to say I want to use a optimization method, or I want to use a simulated dynamics of the craft. How to actually go about it is what we are going to take a look today. Okay, so typically in a trajectory tracking, we are looking at this so-called generating this desired position and attitude. So we are interested in the desired X position, Y position, and what is the yaw angle that I want my craft to be oriented at. Okay, and this is achieved by so-called minimizing the distance between the actual position and the desired position, and as long as that error goes to zero, typically you will have achieved what you want to achieve. Okay, then I think all of this we talked about under actuated and fully actuated systems, and we basically started off talking about the low pass filters. And we understood, and this is where we were. Okay, yeah. So typically when we choose a low pass filter, so the idea of choosing this low pass filter is that it allows for the higher frequencies to be attenuated, and we are looking at a low frequency signal which comes as an output of that system, so that this low frequency signal can be relatively easily tracked. Okay, but at the same time we have to make sure that it's a feasible trajectory, which means that it satisfies the so-called constraints of our vehicle properly, and it can take into account that physical speed and acceleration limits are achieved. So I can't say that I suddenly want to achieve infinite acceleration. That is something which no craft can achieve. So one has to take care that when we generate these trajectories, you have to make sure that that is not the case. So for example, if I'm looking at a trajectory, let's say I'm going like this, and like this, right? A trajectory like that is impossible because whenever the corner point comes across, what's happening, you're changing the direction suddenly at that corner point, which means you're looking at an instantaneous acceleration in yaw, which cannot possibly physically happen. Is everybody understanding what I mean by that? This can be a path following problem. The same path I can give for a path following case and it would be a valid trajectory. But the same thing cannot be given as a trajectory tracking, right? Because when I say trajectory tracking, that becomes a problem because it can't vary smoothly across time like that without having infinite acceleration. Unless until I say that it goes from point A to B and stops there, turns there, and then starts moving around, then it's similar to a path following problem. It's no longer a trajectory tracking problem. Okay. All right, so we also have to understand that there is a compromise to be made. So any design generally requires a compromise. So when we design our so-called control system, we need to make a design compromise between the performance of the control system and how accurate the tracking is. You can make the tracking to be fantastic, but then all the high frequency components also you're tracking, which can be a problematic thing. Or you may have to discard the high frequency things in terms of performance, but at the same time, you'll be losing the effect that you'll be tracking your exact reference signal. So you have to make a compromise between these two typically whenever you're designing either a control system or a guidance system. For both cases, this sort of an application is important. Okay, so typical reference models are motivated by a spring mass damper systems because those are very well understood. We understand them very well in terms of what is happening to the natural frequency or the damping ratios. So it makes sense that when we are trying to generate these so-called reference models for our trajectories, we can take use or fall back upon the spring mass damper systems and tune them to achieve appropriate trajectories that we want to track. Okay, so that's a very standardized approach where that spring mass damper system can be utilized for these purposes. Let's take a look at one of them. And here I'm talking about a so-called velocity reference model, which means that I want to actually track the velocity of the craft based on some reference value which I'm providing. So understand that this looks like a control in the sense that I'm giving some input and I'm looking at some output. But here you have to understand that this reference is being provided to the guidance system, and what comes out is not the actual velocity of the vehicle, but the desired velocity of the vehicle. Okay, and so therefore, when you look at it from far away, you may think, hey, guidance and control, they are like looking the same way, and you wouldn't be wrong in thinking about it. But the idea is here we are looking at the desired trajectory to be the output of the system, okay, rather than the actual velocity of the craft. So with that in mind, a typical transfer function for a spring mass damper system would look something like this. And here we are writing this in the Laplace domain. Okay. I am presuming everyone here is familiar with Laplace transforms to some extent. Yes. I only have doubt about these two fellows. What you call Shadab and Anand. You're familiar?
Basic formulas only.
You know basic?
Formulas, just that much.
But you at least know what is a Laplace transform, right?
Yeah.
We convert from a time domain to a Laplace domain by taking a so-called Laplace transform. It's similar to a Fourier transform. Actually, Laplace transform is a more generalized version of a Fourier transform. If in the Laplace transform I substitute S is equal to I omega, what I end up is actually a Fourier transform. Okay, if you're not familiar with this a little bit, you might want to brush up on it a little bit because it will be useful. maybe what we can do is I may put some material from the maneuvering course, which I'm teaching in the undergraduate level, where we do cover Laplace transforms. So that might be I may put that material up on here in order for you to get up to speed. Okay. So that should help it out more or less to get up to speed. It's fairly simple enough. Laplace transform is not that complicated. We are simply trying to convert it into a different domain. And it only works for linear systems. It does not work particularly for nonlinear systems. So as we go progress in the course and we start looking at more nonlinear control and things like that, you'll observe that these Laplace methods will not be applicable, and we might have to look at new different approaches to solve the problem. Okay, but in any case, where the primary idea is that you are assuming that for a differential equation, you are assuming that an exponential solution actually exists. So if I were to write down, okay, so for example, if for this domain, for this Laplace transfer function, if I wanted to write out the corresponding differential equation in time, it would have been VDI double dot plus 2 zeta omega ni times VDI dot plus omega ni square times VDI times is equal to omega ni square times RIP of t. Okay, so this typically represents a so-called spring mass damper system. If you were to consider, let us say, VDI as the displacement of a spring mass system, then you can simply write this in the more familiar form. F of t, something like that, right? So I'm pretty certain that the bottom equation is something which everybody has seen for a spring mass damping system. Okay, so what we are doing in essence here is we are assuming that since the system is linear, and if my f of t can be assumed to be e to the power st, I can assume my x0, x is equal to x0 times e to the power st. Okay, so if my force is an exponential function, then my displacement can also be assumed to be an exponential function. I'm simply substituting that so-called solution into the differential equation, which gives me the idea that I have s square x naught e to the power st plus 2 zeta omega n x naught s e to the power st plus omega n square x naught e to the power st is equal to omega n square f naught e to the power st. So from this you can see that e to the power st is a common factor which kind of goes away, and you're left with x naught times s square plus 2 zeta omega n s plus omega n square is equal to omega n square f0. I can rearrange this to find out the output by input, which is nothing but our so-called transfer function, which is defining what is the output of the system or output amplitude of the system for a unit amplitude input which I provide, and in which case this simply becomes omega n square by s square plus 2 zeta omega n s plus omega n square. And this is the same transfer function which you saw at this location. These two are the same. That's what we have here, right? So in essence, what I'm saying is I'm taking a differential equation in time. I can convert it into a Laplace domain by assuming a linear exponential solution. And then I'm trying to find out the input amplitude to the output amplitude ratio. So given a particular input amplitude, what happens to my output amplitude? How much output am I getting out of the system? That's what a transfer function is essentially telling me. I'll put up some material on the Moodle in order for you to go through and get comfortable with Laplace transform with some examples as well, so that you can get up to speed on this. Okay. All right. Okay. Notice that in this case, our so-called input here, okay, is some reference value which we provide either using a joystick or a keyboard command or something like that, or it could be even a computer generated signal as an input as well. Doesn't matter. But for the given reference value, we are saying that the actual velocities of the craft which we get out, or the positions of the desired positions of the craft which come out, will come through this low pass filter which we have chosen. Now, by tuning the damping ratio zeta and the omega n, which is the natural frequency of that spring mass damper system, I can play around with what dynamics I want. Okay, that allows me to tune how much input to output amplitude can be varied, or how to vary it. By tuning these parameters, I can make changes to that. Is that making sense for everybody? Especially the graduate students? Yes, no?
Can you repeat it again?
Okay, so the idea here is that when I'm looking at this transfer function, it's basically the ratio of the amplitudes, right? That's what we had here. The ratio, the displacement to the force. And force is my input to the system that results in a displacement of the spring mass system, right? I'm interested in, for a unit amplitude of force, how much response will I be getting? Or what amplitude of response will I be getting? And that is governed by this transfer function. Okay, it really depends on how quickly or how fastly the exponential is dying down, or how slowly the exponential is dying down. For those signals, there will be a difference in the amplitude which you see, because that will depend on the S, right? S determines how fast or how slowly it varies, because it is e to the power st, right? So in that sense, the transfer function is basically telling me what will be the output amplitude for a unit amplitude of force when I choose a particular exponential signal as my input. Is that making sense?
Yes, sir.
Yes. So now the idea is that when I'm looking at the so-called velocity reference model, I'm saying that my input here will be a joystick command or a keyboard input which I provide from my operator. My operator on board the ship, who is trying to dynamically position the ship, is trying to move it, let's say, in one way. His movement will correspond to an actual desired value which will come out of this linear low pass filter which we are choosing, right? How do I tune this filter? I can play around with the damping ratio zeta, and I can play around with the natural frequency, so that I can make the behavior like I want it to be. How should it vary quickly enough? The moment he gives a command, should it immediately respond, or should it respond slowly enough? I can adjust that factor by changing omega. Is that making sense?
Yes, sir.
Yes. So suppose if I want to make the system respond very slowly, what do I want to do to the omega n? If I want the system to respond very slowly, what should I do to the omega n? Should I keep it small or large? Yes, Joel?
Yes, it's a,
Reduce it. If I reduce it, what will happen?
the frequency will be lesser. So, like, yeah, the response speed of the response will be much lower.
The frequency will be, the natural frequency will be lower, but that will cause me to get more response or less response. So maybe let me make this problem a little bit more specific. So let's say that I am looking at versus the frequency. I'm looking at this so-called transfer function, okay, x0 by f0, let's say. So it looks something like this, right? Yes. This peak is where will this peak occur?
At omega.
This will be at omega, right? Now I'm saying that I am giving a signal of some frequency omega 1, let's say. Okay, and I want to make sure that the response of the system is close to 1. It should not overshoot by huge value. Then what should I make happen?
Can you repeat this?
If I want to make sure that the response is not much greater than 1, okay, then what should I do? Should omega n be pushed to the left or to the right?
To the right.
It should be pushed to the right, right?
Yeah.
If I push omega n to the right, what will happen is my system's response, the steady state amplitude which I'll get, will be close to unity. If I push my omega n closer to the left, then my response will be huge. My steady state amplitude will be bigger. Okay, suppose I don't want that peak to be that high. What should I do then? So I don't want that peak to be high.
Make zeta large.
Make the damping more, right? If I increase the damping, what will happen? This curve will start to look more like this, right? And more it will start looking like this. There may be even a point where it starts to look something like this, right? So then what is happening? I'm able to reduce that so-called amplitude distortions. I can reduce them. So I can play around with the damping and the natural frequency to make the shape of this filter, so-called low-pass filter, like the way I want it to be. Okay, so because I may say that there may be certain frequencies beyond which I'm not really interested in more happening. So I may choose those. If suppose I'm looking at the joystick operator is doing a very quick operations, which should not be taken into the account. So I'll try to place the omega n in such a way that all the frequencies of his operation are to the right of that natural frequency. High frequency operations are coming to the right of the natural frequency. Then what will happen when it passes through, his signal passes through that low pass filter, they'll get attenuated.
Sir, could you repeat this part? How do we set the frequencies?
Yes. So suppose I have somebody who is holding a joystick and he's just trying to move it like this, like a crazy kid. Okay. And I want to make sure that my joystick is isolated from such sort of movements. Okay. And I know that he's shaking it at frequency omega 2. Okay. Then I would want to keep my natural frequency of the system less than omega 2. Isn't it? So that these oscillations, they don't figure into my actual desired inputs. Okay, so let's say what I mean by that is if the ship were to suppose track a path like this, and because of his quick movement, it's actually, this is the signal which he would have given as the input. So this is the value of R, but this is the value of Vd that I want. Okay, I want to isolate those omega 2 signal out. So I need to keep my natural frequency of the system to the left of the point where I want it. So that because my RAO will reduce to 0 when I move to the right of my natural frequency, those omega 2 values, whatever amplitude he's giving, it will get attenuated in the signal.
Okay.
Is everybody following me? Anand, you're following me?
Sir, if omega n is lesser than omega 2, what will happen? Like,
If
when
omega n
the
is lesser than omega n, so let us see. Let us take two considerations. Okay, let me try to put this in more perspective. So let's say that this is our curve, which is looking like this. Okay, this is omega, and this is our transfer function h of omega. Let's say. Okay, so and this is my omega n. So in one case, I want my desired velocity. Like this is what I want as an output of my system, right? And my input to the system is the reference value which is provided from the joystick, correct? So let's say that the reference value provided from the joystick ideally is a set point in an ideal condition, okay? Then what should I get as the output? I'll basically take this value of R0, whatever it is, and this thing is nothing but VD0 by R0. So for that particular R0, I will try to figure out what is the value here, and that corresponding VD0 is what I should get as the output. Because this is zero frequency, constant value. Everybody with me so far?
yes, sir.
Yes. Now, the idea is that actually, let us say the signal doesn't look this straight, but it has some slight variations. Okay. Then what's happening? Which means here there are two inputs. One is a flat line. On top of that, there is a sinusoidal variation. Correct? Yes, no?
Sir, why should there be two, sir? Won't the sine be enough? Sinusoidal wave.
Yeah, if it is only a sinusoidal wave, then it should have looked like this, no? Give me a second. All right, yeah. So if it's a pure sinusoidal, this is how it will look, isn't it? A pure sinusoidal signal will start at 0, isn't it? But here I am considering that there is some oscillation about a mean value which is being specified. So then it will be a sinusoidal which is superimposed at some value R0.
Yes, sir.
So I am interested in seeing when I give this signal as an input, what happens to my output. Okay. In one case, let us say that, and let us say that this sinusoidal input's amplitude, okay, is unity. It's 1. Okay. I want to see for a given sinusoid imposed on my reference signal, what is the output that I get. The output also will be sinusoidally varying, right? It will also do something like this. Yes?
Yes, sir.
Right? Now I am interested in what is happening to this amplitude here. I am interested in finding out what is happening to this amplitude A. Okay, that is the point. Okay, and let us say that this oscillation has a frequency of omega 2, which we chose. Okay, or for my case, I'll just call it omega for now, just to make it easy. Now, if this frequency omega lies to the left of omega n, okay, then what happens? It's telling me that whatever amplitude of oscillation is coming in my reference signal will be picked up and it will be given back in the output. Whereas if this omega value was here instead, if it was here, then its amplitude value will be much smaller compared to what I find here. Is that making sense?
Yes, sir.
Right? So in which case what it is saying is, when the amplitude is high enough, it will look like this, but when the amplitude is low enough, if the omega n lies to the right or to the left of the omega value, then I'll see something like this. It will be very flat with very small oscillations. The amplitude of oscillations will reduce.
Sir, in all these cases, the frequency of the output signal will be the same as the input signal, no? In all these cases.
Yes, the frequency will not change because it's a linear system. I can't expect the frequency to change.
Linear system.
Because it's a spring mass damper system. It's linear. The differential equation is linear. There's nothing non-linear about it.
Okay.
Right? Whereas if I am looking at a non-linear system, then funny things can happen. I may give one frequency and I can get something else out of it. Okay? I may get higher frequencies out of it. But that's not what we are discussing here today. Today we are only purely looking at the spring mass damper system. So when I give a certain, so based on where I want to put my omega n will really depend on what sort of inputs I am getting from the reference signal. Which frequencies I want to capture, which frequencies I do not want to capture. I have to make a decision as a control engineer and accordingly choose the location of my omega n, accordingly choose the value of my damping. Okay, so as a control engineer, your task is basically to find out how to figure out the damping and the omega n values given a certain requirement which the owner comes to you with. So the person who is wanting to design the control system will come to you with certain requirement. Okay, I want to track this. Anything beyond these frequencies, I want it to be attenuated. I don't want my gain value to be more than so and so. So all these things will determine how much you are playing with your omega n and zeta. And based on that, the shape of this filter is getting fixed up. So you have complete control on the filter by playing around with zeta and omega n. Okay, that is what is essentially the idea. So that when the reference signal is passed through this filter, it gives you a low frequency signal as an output, which can technically be tracked by your craft without much hesitation. Okay, I hope that's kind of making some sense here. Yes, that's the main idea when we are putting a transfer function which is looking like this. Okay.
Yes,
all
sir.
right. Okay, so we are going to look at the matrix version of this in the next class. So I'm going to stop right here today because I really need to rush out today. So tomorrow we will continue. Maybe we'll have another 15-20 minutes extra tomorrow in order to cover up whatever we have losing time today. Okay. All right. So let me stop recording here.